Woohoo! Welcome back. Today we're going to be talking about doing work and moving water out of a conical tank. And SpongeBob is here because he knows all about working. And we are coming off of the excitement and success of lifting a rope up along a wall. And so, bringing some water up out of a tank, that seems like a really good goal too. This one is going to take some work. So I encourage you to have a calculator and snacks and a drink. And in fact, what I'm realizing is I don't have my pen. Now I have my pen and let's do it. Okay. So here's the problem. A tank has the shape of an inverted circular cone. So that just means it's a cone, like an ice cream cone, and the base is a circle as opposed to some other base shape. It has a height of 10 meters, which you can see there. This is 10 meters, in case it's hard to see on the screen. And the base radius, so the radius of the base is 4 meters. Now, we're pretty excited about this because once you start saying meters, then we're in metric land. We're in Newton land, newtons and joules. So we're back where we should be. None of those foot-pounds for us for right now. Okay, it is filled with water to a height of 8 meters. Now, this is where things start to get a little bit nerve-wracking because you're like, oh no, it's not fully filled. That is fine. We're going to take that into account as we move along. Hopefully we're going to approach this in a way so you're going to look at it, you're going to look at the other problems we did and say, oh, yeah, this isn't too bad. I encourage you, I'm going to write out all the formulas as well, but you may want to have, if you wrote down all the formulas that we've been working with force and work, you won't need Hooke's law because we're not doing springs. But we're going to be talking about mass and density and volume. So if you've got all these formulas written down from the book, it might make it a little easier. I will also write them down here. And I'm definitely going to need a calculator for this one. Okay, you guys ready? Woohoo, let's do it. So right off the bat, the book has decided the gloves are coming off on this problem, and that's okay. And so I'm going to introduce you to the concept that there is no orientation in math that is required. We have axes, but we can position them as we need. And to change the subject slightly, I want to ask the question, if you're watching a show about space, and we're talking about this, outer space, the universe, why in the world would any two, and here I'm going to have trouble drawing a spaceship. So I'm going to draw the spaceship like this, with a little window at the front. There we go. Spaceship. There we go. There's a little propulsion. There's the spaceship 1. And that spaceship has just come off of one planet. Why do we always visualize that every other spaceship that they encounter faces the same way? This is a universe where everyone makes the same spaceship. Why would spaceships be the same orientation up? If you leave a planet this way, you'd be facing up. But if you're on the planet down here, if you leave the planet from the bottom, and you come off the planet then you would be facing the other way. Now, in space, gravity is kind of beside the point. If you're out in the middle of space, you're presumably in a ship that has somehow created its own sense of gravity. That's most of the TV shows about science fiction talk about that. So there is an up and a down in the spaceship itself. But depending on where you launch from on a planet, you wouldn't necessarily, this person thinks this is up, this person thinks this is up. Someone who left from over here would think a completely different direction is up. And then you go flying around the universe. When you meet, why would you meet facing the same way? And so all of that, which I'm giving you, is something to think about tonight. It's like, why would you assume that you'd be facing the same way? All of that is to say, the book has decided, as I said, the gloves are off, and the book is now drawing a picture of the cone. The water is at the bottom of the cone because gravity is pulling down this way. And it's technically accelerating down that way, but you know what I mean. And they're going to call this X. And we're all going to take a deep breath and we're going to say, you know what? This is what I'm saying right here. The book imagines this cone lying along a vertical axis, which is X. If this really bothers you, you can orient your picture so that X stays horizontal. What I'm going to suggest to you is that most important in a problem is if you decide that this distance, so we're going to cut out a little disc of water at a depth of X sub I. So if X is going up and down, then for our little disc of water, this little width or depth of that disc is in the same direction. So it's delta X. Does that make sense? Now, if you wanted to, you could do everything in Y. If you're just like, no, X cannot go this way, perfectly fine. That's reasonable. I'm just explaining this is what the book has decided to do. So if you want to make these all Y's, you rock on with your bad self. Make them all Y's. If you want to make them Z's, if your name starts with, the letter K, for example, and you want to make it all K's because you're like, where are all the K's? You could do that. So it's totally up to you what variable you use as long as you're consistent. So let's look at this image and let's make sure we agree. So from the top, what we're considering the top of this tank, down to this disc of water, that distance we're going to call X sub I. The whole distance is 10 meters. So what is left, this right here, is going to be 10 minus X sub I. Because this part is X sub I, the whole thing is 10. So this has got to be what you get when you subtract the two, right? It's the difference in the two. So we've got that. We know that the water starts 2 meters down. We know that the radius at the base, which is technically at the top, is 4 meters. So do we know what the radius is of a generic disk? And the answer is we don't. So for now, we're going to call this R sub I, which is written right there. But again, it's pretty small, so I think you can't see it. So just a generic disk of water is down X sub I, and the radius is R sub I. Now, if you've been playing math for a long time, you'll know we can't do this. We got X's running around, and then suddenly to introduce another variable is going to make it nearly impossible to do. So we're going to have to come up with a way to figure out what the radius is in terms of how deep this is. But first, the book wants us to go through the disk. So let's talk about it. Slice the 8 meters of water into disks of width delta X. That's what I've got up here. That's what that is. All the water in each disc has to be raised approximately the same distance to pump it up and out of the tank. So remember, when you're talking about work, work is a force times a distance, right? It's one of the basic formulas. It's that second one. Work is force times distance. And so what we want is we want to find all the bits of water that travel the same distance. And so the book is claiming if you take this little slice of the water and you make delta X really, really small, all of that water travels up a distance. Now, how far does it travel up? It travels up X sub I. So each disk, the ith disk, travels up X sub I. Okay. Next up, we need the volume. The volume of this disk, remember this is delta X, the width or depth of this. We have said the radius is R sub I, and so basically we've got a cylinder, right? So it's pi times the radius squared times how tall it is. Right? So normally the volume would be pi r squared times the height, but here we've got r sub I because they're all different radii, and the delta x is how tall it is. Okay, so there's the volume. And now we say we need to figure out r sub I equals, what is it even? Okay, you ready for some mathematical, no, that's not going to work. Mathemagical amazement. I know. So is SpongeBob is so excited. You guys are going to have to imagine because I promise not to try to make him laughing. Okay. Dun, dun, dun. Everything's old is new again. So what is the foundations? What are the foundations of math? Foundations of math are the algebra we use and the geometry, which was first observed and studied thousands of years ago, right? So what is this a drawing of? Well, a cone is basically a triangle, right? If you slice it down the middle. And here's the radius at the top. This one's 4 meters. We've got our little slice down here that's r sub I. Yeah? We know the whole height of the cone is 10 meters. And we know that this is down x sub I. So this little piece that's left is 10 minus x sub I. Now, a lot of times when you see triangles, you immediately go to Pythagorean theorem. And that's great if you need to know something about the diagonal, if you need to know something about the hypotenuse. But we don't know anything about the hypotenuse, and we're not really looking to find out anything about the hypotenuse. What we want to do is we want to find out one of the legs. And if you're looking for the legs and the hypotenuses are not involved, then the next place you want to look is similar triangles. And basically, the similar triangle says, I've got the super big triangle that has 4 here and 10 here is similar to the little wee baby triangle that's right there. This is r sub I, and this is 10 minus x sub I. So what are we talking about? We're talking about this being the big triangle, and then this being the wee bitty bit of the triangle. Now, why are they similar? It's a fair question. They are similar because they have basically matching angles, but matching attributes. This is a right angle and this is a right angle. These are both right angles there. This, whatever this angle is, since they both share it, I'm going to call it the one with the single dash like that, they both share it. So these two angles match. Now, if they both have right angles and this end point, this tippy top angle is the same, of course, this angle would have to match this angle. They have to be, because every triangle, right, the sum of the angles in a triangle is 180. So if two of the angles match, the third one also has to match. So when you've got two triangles that are basically, it's just a big version and a little version of the same triangle, then you can start setting up ratios. And that's what we've got here. That's what similar triangles mean. So 4, that's the base, which is at the top. I know it's kind of goofy, it's upside down, to the long leg, right? So the short leg to the long leg is 4 to 10. So in the little guy, the short leg is r sub I, the longer leg is 10 minus xi. And now we've got this, and we've set two ratios equal to each other. We've got a proportion. And so now we can solve, we've got an equation basically that has r and x together. And as soon as they're together, we can compare them to each other. So, woohoo. If I multiply both sides, you know what, I'm going to get rid of this. So it made sense with English, but I want to use the space to write down, I'm going to multiply both sides by 10 minus x sub I. And then this cancels here, right? And then I get r sub I equals 4/10 times 10 minus x sub I. Do you guys agree? Okay. And then this is going to be equal to 2/5 times the quantity 10 minus x sub I. You can also write this as 0.4. It works out. This is a nice decimal. A lot of times mathematicians tend to keep things as fractions because you never know when fractions are going to go sideways on you. And so, depending on having to use decimals, that it's kind of shady sometimes, because if thirds show up, if sixths show up, you know the party's going to go south. So generally we try to keep things as fractions, but in this case, perfectly welcome to go ahead and move into decimals if it's more comfortable. I'm going to go ahead and figure out what r sub I squared is, because remember, I need not just r sub I, but I need to know what the radius squared is to find that volume of the little piece of water, which is a really weird thing to say, but also kind of cool. So that's going to be 2/5 times the quantity 10 minus x sub I, the quantity squared, and that's going to be 4/25 times the quantity 10 minus x sub I squared. Now, if you would like to, you can go ahead and multiply this out now. I'm not going to do it quite yet. I've already written a bunch of the stuff in, so, but feel free to jump ahead in the work. And basically then I have to remind myself that the volume of the ith little disk of water, right, was pi r squared h, which was pi times ri squared times delta x, right? So here we are, pi times the 4/25 times 10 minus x sub I squared, that right there. So this right here is what's right there. There is a pi added in right here because we have pi r squared to get that circle. And then this delta x, this is the height of that little disk of water. This is some hardcore geometry, but it's kind of satisfying, right? It's pretty cool that we can do this. I love this. Now, let's not discuss whether or not humans can actually build a conical tank that is exactly conical so that all the math works out perfectly. The good news is there are engineers. Engineers figure that stuff out. The mathematicians, we get to live in a world where we can make perfectly conical tanks and we don't have to worry about it. There's no such thing as materials or pressure or anything like that. We don't have to worry about it. It's awesome. Join us. Become mathematicians. We don't have friction. It's a glorious place. Okay, so you guys ready? There's one more surprise. Yay! Surprise! Yay! Okay. So, we got to figure out what the mass of the disk of the water is. We need to use the density of water along with the fact that mass is density times volume. Yeah, another formula. The good news is if you have to do a problem like this on the test, I will give you these formulas because, yeah, these are physics. But this one, I want to try to convince you this one is actually not completely out of left field. So mass, I've told you, is the total amount of stuff. It's all the stuff. What is density? Density tells you how much stuff there is in a particular space. So if I have this much space, the density tells me how tightly packed the stuff is. And things like water or steel or glass have a constant density. Their solids have a density that's we can predict and we understand. Gas gets a little bit weird, but we're not doing gases, thankfully. Yay. So this is water. And so water has a density, and that tells us how much stuff, when you look at water, if you take a bit of water, it will tell us how much stuff per volume we have. So if we know how much stuff per volume, and then we multiply by the total amount of volume, that tells us the total amount of stuff. And hopefully all the physicists aren't rolling in their graves right now, but I totally understand if they are. So that was my Catherine's suggestion about how physics works. Okay, let's come back from that. Let's go back to math. So it turns out that the mass, the density of water, we can measure as 1,000. So we've got 1,000 times the volume, which is 1,000 times the result that we got in the previous page. So that was the 4 pi over 25. Here's the r squared, 10 minus x sub I, the quantity squared, delta x, right? There's the height, there's the radius, there's the pi, and here's the density. Woohoo! Okay, so isn't it lovely that we're dealing with such lovely round numbers, because the 25 and the 1,000 are going to cancel. And I believe we get 40 times 4 pi times this thing, which honestly we're going to have to deal with. We're just putting it off for right now. So altogether I get 160 pi times 10 minus x sub I squared delta x. Pardon me. SpongeBob. Okay. And finally, now what is this? This is the mass. We need to find the force. The force is the mass times the acceleration. And in this case, and it's always funny because it says acceleration. It's like, how fast is that water going? It's not. It's getting pulled by the acceleration of gravity. So it's just gravity, 9.8 meters per second squared. And so 9.8 is the gravity. So here, gravity is the 9.8. And the mass is this thing we just did up here. All right, that's this guy. And this is just the mass of that little chunk of water. At this point, you may be feeling a little bit nervous about these. So the first thing is, this is a word problem. Word problems are well known to be very complicated. However, I want to try to convince you that if you go back, and this one might take a couple of watches or working through on your own, but if you go back, each piece builds up. They build and they build, and if you follow the formula, so it takes a long time to get here. So we had to start with the volume, then we went to the mass. From the mass, we find the force, and of course, there's going to be another step because from the force, we find the work. So it is a logical progression though. So first time through, it's going to feel like, oh my goodness. But if you look at it again, give yourself some time, come back, you'll be like, okay, there are steps to this. These are puzzles, and each puzzle piece fits in, and we just make it bigger and bigger till we get to where we need to go. Okay, so this is the force that ith chunk disk of water is experiencing. And then remember that ith chunk needs to be pulled up x sub I. So 9.8 times 160 is 1568. I've already done this multiplication. There's the pi. There's the pi. This should say x sub I. Sorry about that. I will fix that. 10 minus x sub I, the quantity squared, delta x. And this is it. This is the work that it takes to pump that ith disk of water up and out. Okay, so the total amount of work, don't worry about the limits for right now. It's going to be 1568 pi times x sub I, 10 minus x sub I, the quantity squared, delta x. Okay, now, hopefully this one you'll be like, oh my gosh, I've got it. But just in case you're not, let's take a look. Why do we start at 2? Why does it not start at 0? That is a fair question. Like all the others started at 0. Like the rope or the cable, you went from 0 to 100. Why is it 2? Remember the little sneaky bit that we didn't fill the water all the way to the top? We actually only filled it up to 8 meters deep. And so the first disc right here does not have to go 0. It has to go 2. And then the last little disc, this little disc that's right there, that has to go the whole 10 meters. So we start at 2 and we go all the way down to 10, how far it needs to go. Okay. You did it. We did it. We're there. Now, have we solved the problem? Not quite. We actually have to do the calculus. But again, I am hoping that the calculus here, and in fact, I just realized I did something terrible to you. What did I do? I was so excited. Can you guys see the mistake? I was so excited. Each individual disk has this work. But when we put it into the integration, do we do sub I? And the answer is no. We just consider it x. So I am so sorry. I don't know if you guys were like throwing things at your screens going, wait a minute, why are you putting the i's in? The answer is because I was distracted by the beauty of the physics. That can happen. It can totally happen. So I'm sorry about that. Didn't mean to be confusing. Okay, you guys ready? Now it's math. So we bring in the mathematicians. Okay, here we come, like the cavalry. So what am I going to do? First thing I'm going to do is I'm going to chuck this big chunk O constants outside. You wait out there. We're going to sort this out. We'll be back to get you in a second. Oh my gosh. Oh my gosh, heads will roll. What else did I do? I just fixed it here and that made me notice. So we don't, oh my goodness. But I just want to point out, as long as you've got, I like the Tombow. There's another one that I really like and I can't remember the name. It's better, but I don't have it with me. As long as you have some whiteout or an eraser, I just want to point out, if you make a mistake in math, that's it. No lightning, no shame. I mean, I feel a little silly, but I'm already 29 minutes into a video. I'm not going to re-record it. I'm just going to say, I'm so sorry. And I'm going to point out where my mistakes are and say, did you catch that? And those of you who did, awesome. You guys are eagle-eyed. I'm sure SpongeBob Probably, I don't know. You guys can decide whether you think he saw them, but he's like, no, everybody's good. You just fix your mistakes and move on. Okay. So now that I'm looking at this, I think I got it. I don't think I have any more mistakes. Obviously, if I do, let me know. And now's the time when we have to multiply this out. Really, if you have been holding out on learning how to square something, pardon me, SpongeBob, a minus b, the quantity squared, is a squared minus 2ab plus b squared, right? So have that formula memorized is what I would recommend. Now, if you don't have it memorized, you're going to have to multiply out using FOIL. Or if you have another multiplication, like you use the chart or the lattice method or one of the other methods, you're going to have to do that. So that's between you and your gods, honestly, however you want to multiply it out. But I'm going to tell you, we square things so often in math, it's worth memorizing. So I happen to know this by heart. 10 squared minus 10 times 2, I reversed that, sorry about that, plus x squared dx. So then I get 1,568 pi times the definite integral from 2 to 10 of 100x minus 20x squared plus x cubed all dx. Take a look at that. Let's make sure I got that right. Okay, so now that's 1568 pi. And I'm going to go ahead and integrate. 100x becomes 100 times x squared over 2. The minus 20x squared becomes minus 20x cubed over 3. And x cubed becomes x to the 4th over 4. And we're going to have to evaluate that between 2 and 10. So far, so good? Okay, do I have another piece of paper? Yes. Okay, so take a look there. Okay, I'm going to go ahead and copy this over. I'm going to make a few adjustments. This is 1568 pi times the quantity, and this is 50x squared minus 20x cubed over 3 plus x to the 4th over 4 between 2 and 10. So far, so good? 1,568 pi times. Okay, here we go. 50 times 10 squared minus 20 times 10 cubed over 3 plus 10 to the 4th over 4 minus 50 times 2 squared minus 20 times 2 cubed over 3 plus 2 to the 4th over 4. Okay. $50 times 10 is 500 times 10 is 5,000. This is 10 cubed is 1,000 times 20. This is 20,000 over 3. And then 10 to the 4th. Hopefully you know that trick. You just, whatever, if it's 10 raised to a number, it's that many zeros. Two squared is 4, so this is going to be 200. 2 cubed is 8 times 20 is 160 over 3. 2 to the 4th is 16 over 4. So you may be asking yourselves, why did I not use the magic of television here? And the answer is, I realize a lot of times I do just say, and magically here's the answer. And I did not want to do this time because I wanted to make sure you saw that these problems take a lot of work, and it's just grinding it out. At the end, definite integrals are definitely integrals. Are there shortcuts I could be making? Absolutely. And if you like some shortcuts, use them. Let's make sure we all get the same answer. So I think I get 5,000 minus 20,000 over 3 plus this. I can simplify. 10,000 divided by 4 is 2,500. This is going to be minus 200 plus 160 over 3 minus, and this is going to be 4. This is 1568 pi times the quantity. Okay, 5,000 plus 2,500 is 7,500 minus 200 minus 4. So this is going to be 7,296, I believe, right? 7,500, 7,300, 7,296. At this point, you may want to use your calculator. These thirds are just the bane of our existence, yeah? So you've got minus 20,000 over 3 plus 160 over 3. And they're not even in the same magnitude, you know? They're just so far off. So at this point, I think a lot of folks in physics and engineering, if not sooner, would have just put it all into a calculator and started rounding. The difference between sometimes physics and engineering and math is that math is dedicated to going to the bitter end. Even if it takes us 3 more hours, we're going to get an exact answer. And then that exact answer can be rounded however you like. But we want to keep that purity so that we can know that our answer is going to be, you know, as close as possible. Now, what are the when does this not work? And the answer is, well, a lot of times some of the numbers that go into the problem are already rounded. And if that's the case, then coming up with an exact answer, it may be a little bit foolish, but it's the closest we can get. So this is always going to be the standard that math aspires to, even if we don't actually achieve it, is use the numbers we have and come as close to the exact answer as we possibly can with the numbers we have. Okay, so we've got some choices. We can try to estimate this. We're going to end up with thirds. That's always very dangerous because that would be a 0.3 repeating or maybe a 0.6 repeating, depending. The other option is to put everyone up over thirds, which I think is actually the way we're going to go. So this is 1568 pi. Gosh, they've been waiting outside for the longest time. Oh, on. That scared me. My calculator was like, sorry, nope, don't want to do this. 7,296 times 3. So I've got 21,888 over 3 minus 20,000 over 3 plus 160 over 3. Okay, so I'm just going to play with the numerator. I've got 21,888 from multiplying this by 3 to get it up over thirds. And so then I subtract the 20,000 and I get 1888, not surprising. And then I add 160. Could you do this in your head? Absolutely. Could I do it in my head? Not sure. Dyslexia is a tricksy guy. Sometimes it's not a problem, and sometimes, it's a problem everywhere. It's just never really know. Okay. Almost there. So what do we do with pi? Pi is a transcendental number. There is no equivalent value that is exactly correct. Anytime you express pi as a number as a human, you come up with a rounded answer. So the best we can do is just to leave it as pi. So I'm going to go ahead and leave the pi in, and I'm going to take the 2048 and multiply by the 1568. That is quite a number. 3211264 all over 3 times pi. So 3,211,264 over 3 times pi. Now I put the commas in there so you could read it. In reality, we don't tend to use commas up in a fraction. It's just distracting. So we write it like this. How much work is involved in emptying that tank? There you go. And that's going to be in joules, Newton meters. And we got it. You guys are awesome. That's amazing. Oh my gosh. Second longest video ever. You guys made it. Congratulations. SpongeBob says, yay, we're done with work. So now the good news is that the rest of the semester we can all joke around and say, at least this isn't work. So there you go. Hopefully it made sense. Again, if you're in class with me in person, I will have this sheet of physics formulas. I'm not sure if it may get longer before the semester is out, but you'll have a bonus free physics formulas. I know all the kids are going to want to take this class now. And just keep practicing. Ask for lots of help. This section is possible. I know it was the bane of my existence when I was in school, but I made it through. So you can make it through too. You guys are amazing and awesome. Go rest. Take a break. Please don't watch any more videos right now. Please go touch some grass if you can, or touch the rain, or whatever you can touch that's away from this screen that you're using. Please go do that. Wiggle your body, move around, get a snack or a full meal, Tell someone you love them. And I will see you guys in the next video. Woohoo! You guys are amazing. Yay! Math on. Woohoo! May the force be with you.